There is a particular kind of quiet that lives on mountaintops. Not the quiet of a room with the door closed, or the quiet of a library in the early morning hours. Not even the quiet of a forest trail before the birds have started. This is something different, something older and deeper and more indifferent to human presence.
The dot was extremely faint. Its apparent magnitude, the astronomer's measure of brightness as seen from Earth, was 17.8. To put that in terms that mean something without a degree in astrophysics, the faintest stars you can see with your naked eye on a perfect dark night are around magnitude 6. Every step of one magnitude corresponds to a factor of about 2.5 in brightness. So, a magnitude 17.8 object is roughly 100,000 times dimmer than the faintest thing your unaided eyes can detect. You would need a serious telescope in a seriously dark location to even know it existed. The automated systems flagged it. The data was transmitted to the Minor Planet Center, the International Clearinghouse for New Solar System Object Discoveries, operated out of the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts. The report arrived there at 7:48 in the morning Universal Time. And then, because this is how modern astronomy works, the alert went out to observatories around the world. And people started looking. What they found in the hours and days that followed would change the way we understand our place in the galaxy. But we'll get to that. We'll get to all of it, slowly, carefully, the way these things deserve to be told. Tonight we have time. Tonight there is nowhere to go and nothing urgent to attend to. Tonight the story can unfold at the pace the universe actually moves, which, when you think about it, is both very slow and very fast, depending on where you're standing and what you're watching. So let's not rush. Let's start instead with a question. A simple question that turns out to have a very complicated and very beautiful answer. What is a comet?
Part 2. Dirty Snowballs and Ancient Messengers. Humans have been watching comets for as long as there have been humans to watch. Long before we had any idea what they were. Long before we had telescopes or spectrographs or spacecraft or any of the instruments that now let us peer into their chemical hearts, we watched them move across the sky and we felt things. Awe, mostly. Fear, often. A sense that something significant was happening, that the cosmos was communicating something urgent and important, even if we couldn't quite decode the message. Ancient Chinese astronomers cataloged comets with meticulous care. Babylonian scribes recorded their appearances on clay tablets. Greek philosophers argued about their nature. Were they atmospheric phenomena like clouds or lightning? Were they escaped planets? Were they signals from the gods? The Roman senator Pliny the Elder described comets as threatening and malignant, signs of war and pestilence and the fall of kings. Shakespeare put comets in the mouths of his characters as harbingers of death and upheaval. Julius Caesar died, and a comet appeared in the sky, and people made meaning from the coincidence. For most of human history, comets were portents. They were messages. They were things that didn't belong in the orderly, predictable machinery of the heavens, and their appearance, therefore, signaled disorder, disruption, change. It took a long time for us to realize that we were, in a very deep sense, right, though not in the way we thought.
The breakthrough came in stages. Edmund Halley, in the early 18th century, applied Newton's newly formulated laws of gravitation to historical comet records and realized that certain comets appearing in 1531, 1607, and 1682 were the same object, following the same highly elongated orbit around the Sun, returning approximately every 75 to 76 years. He predicted it would return in 1758. He didn't live to see it, but it came back exactly when he said it would. And the comet that still bears his name became the proof that these celestial wanderers were not supernatural visitors, but natural objects, objects with orbits, objects bound by the same laws of gravity that kept the Earth circling the Sun. Over the next 2 centuries, we built up a detailed picture of what comets are and where they come from. The basic anatomy became clear. At the center of every comet is a nucleus, a solid body made of ice, dust, and rocky material, typically ranging from a few hundred meters to a few tens of kilometers across. When a comet passes close to the Sun, the heat causes its ices to sublimate, to transform directly from solid to gas without passing through a liquid phase. This outgassing creates the coma, a diffuse atmosphere of gas and dust that surrounds the nucleus and can extend for hundreds of thousands of kilometers. The solar wind and radiation pressure push the coma's material away from the Sun, creating the comet's iconic tail, or rather its 2 tails, because there is always a dust tail which curves gently along the comet's orbital path, and an ion tail which points directly away from the Sun regardless of the comet's direction of travel. The dirty snowball model, proposed by astronomer Fred Whipple in 1950, captured the essence of this picture. Comets are, roughly speaking, dirty snowballs, icy nuclei made of water ice and carbon dioxide ice and methane ice and a whole chemistry of frozen volatiles, mixed with dust and rock and complex organic molecules. They are relics of the solar system's formation, material that was never incorporated into a planet, that spent billions of years in cold storage in the outer reaches of the solar system, that only reveals its nature when it ventures inward and the Sun warms it into activity. We now know that most of the comets that visit the inner solar system come from one of 2 reservoirs. The Kuiper Belt, a disk of icy objects extending from just beyond Neptune's orbit out to about 50 astronomical units from the Sun, supplies the short-period comets, the ones that return on timescales of less than 200 years. Halley's Comet, with its 75-year period, is technically classified as a short-period comet because it was captured into a relatively tight orbit by gravitational interactions with the planets long ago. Beyond the Kuiper Belt lies the Oort cloud, a vast, roughly spherical shell of trillions of icy bodies extending from perhaps 2,000 astronomical units to perhaps 100,000 astronomical units from the Sun. The long-period comets, the ones that take thousands or millions of years to complete a single orbit, come from the Oort cloud, nudged inward by the gravitational perturbations of passing stars or the tidal forces of the Milky Way galaxy itself.
These are our comets, solar system comets, born in the same disk of gas and dust that formed the Sun and all the planets, shaped by the same processes, carrying in their ices the chemical record of the conditions that existed 4.6 billion years ago in the cloud of material that became our solar neighborhood. They are messengers from our own deep past. And for centuries, they were the only kind of interstellar messenger we knew about. But then we started wondering, what about comets from other solar systems? If our solar system ejects comets into interstellar space, and it does regularly through gravitational interactions with the planets and passing stars, then other solar systems must do the same thing. There are somewhere between 100 billion and 400 billion stars in the Milky Way galaxy. Most of them formed from protoplanetary disks similar to ours. Most of them, presumably, ended up with reservoirs of icy debris similar to our Kuiper belt and Oort cloud. And if they're ejecting material into interstellar space, then the galaxy must be full of these wanderers, icy rocks from other solar systems, drifting between the stars, crossing paths with stellar neighborhoods they were never born in. For decades, this was just a theoretical prediction, a compelling prediction backed by solid physics, but impossible to test because we hadn't yet detected a single one of these interstellar wanderers passing through our own solar system. That changed in October 2017 when a faint point of light moving through our solar system on a hyperbolic trajectory announced itself to the Pan-STARRS telescope in Hawaii. Its name was 1I Oumuamua, and it was the first messenger from another solar system we had ever caught in the act.
Part 3. The First Visitors, Oumuamua and Borisov. Oumuamua, pronounced Oumuamua, a Hawaiian word meaning roughly a messenger from afar arriving first, was unlike anything astronomers had prepared themselves to see. It was detected after it had already passed its closest point to the Sun. By the time Pan-STARRS caught it in October 2017, Oumuamua was already on its way out of the solar system, moving away from the Sun at a speed of about 87,700 kilometers per hour. The detection came almost by accident, a lucky catch in survey data that happened to be processed at the right moment. And from the very beginning, Oumuamua was strange. The first strangeness was its shape, or rather our inferences about its shape, because we never resolved Oumuamua into anything other than a point of light. What we could measure was how its brightness varied over time. As it tunneled through space, rotating on some complex axis, it became brighter and dimmer in a regular pattern. The amplitude of that variation was extreme, about a factor of 10 in brightness, cycling every 7.3 hours. For an object to vary that much in brightness as it rotates, it has to be dramatically elongated, like a cigar or a pancake, with a length-to-width ratio of at least 5 or 6 to 1, possibly more. We were looking, apparently, at the most elongated natural object ever detected in the solar system, something that looked less like the roughly spherical or gently irregular shapes of familiar solar system objects, and more like something you'd find in a science fiction novel. The second strangeness was the absence of a coma. Oumuamua showed no signs of outgassing, no cloud of dust and gas,
no tail. For an icy body passing relatively close to the Sun, this was puzzling. Solar system comets typically develop vigorous comas when they venture inside the orbit of Mars. Oumuamua came much closer than that, inside the orbit of Venus at perihelion, and showed nothing. Either it had already lost all its surface volatiles during billions of years in interstellar space, or it wasn't icy in the conventional sense, or something else was going on. The third strangeness, which only became apparent after careful analysis of the trajectory data, was the most unsettling. Oumuamua was accelerating. Not the way a comet accelerates by falling toward the Sun. That's gravity, perfectly predictable, perfectly understood. This was additional acceleration, beyond what gravity alone could explain. A subtle but measurable push acting on Oumuamua as it moved away from the Sun. The pattern of this extra push was consistent with what you'd expect from the pressure of sunlight acting on a very thin, very flat, highly reflective object, something like a solar sail. Or it could be from the outgassing of invisible hydrogen ice, which would sublimate without producing a detectable coma. The jury is still out years later. The honest answer is that we don't fully understand what we saw. Oumuamua left our solar system before we could study it properly. We had only weeks of observations. We couldn't send a spacecraft. It was moving too fast. It had a head start, and our propulsion technology isn't even close to capable of intercepting something moving at that speed. So Oumuamua slipped away into the dark, carrying its mysteries with it, leaving astronomers with a head full of questions and a fierce hunger for the next one.
They didn't have to wait too long.
On August 30th, 2019, amateur astronomer Gennady Borisov, observing from his private observatory in Crimea, spotted a fuzzy object moving through the constellation Cancer. Borisov reported it to the Minor Planet Center, and within days, analysis of the trajectory confirmed the exciting truth. This was the second interstellar object ever detected passing through our solar system. It was named 2I Borisov in his honor. Borisov, in almost every way that mattered, was the anti-Oumuamua. Where Oumuamua was weird and inexplicable, Borisov was reassuringly normal. It had a coma. It had a tail. It outgassed water vapor and carbon monoxide and other volatiles in proportions that were, more or less, consistent with what you'd expect from a solar system comet. Its shape was compact and roughly spherical, typical of ordinary cometary nuclei. Its light curve was unremarkable. The Hubble Space Telescope observed it and found a nucleus roughly half a kilometer in diameter, small but not bizarre. Borisov was essentially a comet from another solar system that behaved like our comets, which was, in a way, exactly what theoretical models had predicted. If other solar systems form like ours, their comets should be roughly similar to ours. The same basic physics, the same broad chemistry. Water ice and carbon dioxide and rocky dust and organic molecules, the universal ingredients of comet formation. Borisov's very normality was scientifically valuable.
It suggested that the processes that form comets, the aggregation of icy planetesimals in the cold outer reaches of protoplanetary disks, are universal. That water ice is a common constituent of cometary material across the galaxy. That the building blocks of life, the same molecules that comets may have delivered to early Earth, are being manufactured and distributed everywhere stars form. But Borisov also, like Oumuamua, got away before we could really study it. It too was gone before any spacecraft could be scrambled. It too became data and archives and published papers and a hunger for the next one. The scientific community understood what this meant. The era of interstellar visitors had begun. With better telescopes, better automated sky surveys, better detection algorithms, we would find more of them. The question was not whether, but when. The answer, as it turned out, was July 1st, 2025.
Part 4. The Discovery. Let's go back to that mountain in Chile. The Atacama Desert is one of the driest places on Earth. In some parts of the Atacama, rainfall is measured in fractions of a millimeter per year. Some weather stations in the high desert have never recorded rain at all, not a single drop, in decades of continuous measurement. The air is extraordinarily dry and thin and transparent. This is why the world's major observatories are clustered here. The Very Large Telescope, the ALMA radio array, the Gemini South Telescope, and, less glamorously but no less importantly, the Atlas Survey Telescope that sits on Cerro Tololo at an elevation of about 2,200 meters, scanning the sky with automated patience that no human observer could match. On the night of June 30th to July 1st, 2025, the Atlas telescope was doing what it does on every clear night, sweeping back and forth across the sky in a programmatic pattern, capturing images, stacking them, comparing them to reference images taken on previous nights, and running an automated pipeline that flagged any source of light that had moved between observations. The sky over Cerro Tololo was clear that night. The seeing, the astronomer's term for the steadiness of the atmosphere, which determines how sharp the images are, was good. The moon was in a phase that kept it out of the critical observing windows. Conditions were about as good as they get. And somewhere in that sweeping gaze, on a patch of sky in the constellation Sagittarius, near the rich, crowded star fields of the galactic center, a dot of light was moving at a rate that the automated pipeline flagged as unusual. Moving at a speed and in a direction that didn't immediately match any known solar system object. The pipeline generated an alert. The alert was packaged with the relevant data, position, brightness, rate of motion, time of observation, and transmitted to the Minor Planets Center in Cambridge. It arrived at 7:48 Universal Time on July 1st, 2025.
What happened next is a testament to how modern astronomy works and why it works so well. Within minutes of the report arriving at the Minor Planets Center, the data was made available to observatories around the world. Astronomers who were still awake started looking at the data.
Automated systems at other observatories started scanning their own archives for pre-discovery observations of the same object. And very quickly, the picture began to clarify. Pre-discovery observations were found in data from the Zwicky Transient Facility at Palomar Observatory in California, images taken on June 28th and 29th that showed the same object. Then, ZTF images from June 14th to 21 were identified. Then, Atlas images from June 25th to 29th that the pipeline had missed. And ultimately, an amateur astronomer named Sam Dean tracked down additional Atlas pre-discovery observations stretching back to June 5th, 2025. So by the time the object was officially announced, it had been sitting in the data for nearly a month. The reason it hadn't been spotted earlier? It had been passing in front of the galactic center, the densest, most crowded star field in the sky. Against that backdrop of thousands of closely packed stars, finding a faint moving dot required exactly the right combination of image quality and detection algorithm. And that combination had finally come together on the night of June 30th. As pre-discovery observations accumulated, astronomers began fitting an orbit to the data. They needed to determine, was this object bound to the Sun, or was its trajectory hyperbolic? The answer came back quickly. It was hyperbolic, but not mildly hyperbolic, not just barely above the threshold that would indicate an interstellar origin. The preliminary orbital solution gave an eccentricity that was, by any measure, extraordinary. The number that emerged from the orbital calculations was 6.141, an eccentricity of 6.141.
Let's take a moment to really absorb what that number means, because it's central to everything that follows. The eccentricity of an orbit is a measure of how non-circular it is. A perfectly circular orbit has an eccentricity of 0. An elliptical orbit has an eccentricity between 0 and 1. Earth's orbit has an eccentricity of about 0.017, nearly circular. Halley's Comet has an eccentricity of about 0.967, very elongated, but still less than 1, still a closed ellipse, still bound to the Sun. When an eccentricity exceeds 1, the orbit is a hyperbola, an open curve. An object on a hyperbolic orbit is moving faster than escape velocity, and it will never return. Oumuamua had an eccentricity of about 1.2, clearly interstellar, but relatively modest. Borisov had an eccentricity of about 3.36, high, clearly interstellar. 3I-Atlas 6.141. The trajectory was so hyperbolic that the object's path through our solar system looked almost like a straight line. The Sun's gravity barely bent it at all. This was an interstellar bullet fired from somewhere in the galaxy, crossing our solar system on a trajectory so extreme that it announced its foreign origin with unmistakable clarity. The Minor Planet Center made it official on July 2, 2025, the designation 3I-Atlas. The 3I means what it says, third interstellar, the third confirmed object ever detected passing through our solar system from somewhere else entirely.
and Atlas, of course, for the telescope that first brought it to our attention, the watchman on the mountain that was looking for danger and found instead a wonder.
Part 5. The speed of things. Here is where I need to try to communicate something about scale that is genuinely difficult to convey in human language. Because the numbers involved in 3I-ATLS's journey are so far outside ordinary human experience that the words we use for them tend to slide off the surface of the mind without sticking. So, let's try to make them stick. When 3I-ATLS was first detected on July 1st, 2025, it was traveling at approximately 137,000 miles per hour relative to the Sun. That number, 137,000 miles per hour, is its speed at that moment inside Jupiter's orbit, while our Sun's gravity was already beginning to accelerate it further as it fell inward. Let's try to put 137,000 miles per hour into some kind of human context. The fastest commercial aircraft in regular service typically flies at around 600 miles per hour. The fastest military jets can reach around 1,500 to 2,000 miles per hour in short bursts. The fastest human-made rocket-powered aircraft ever flown by humans, the X-15 in the 1960s, reached about 4,500 miles per hour. The Space Shuttle, during orbital operations around Earth, traveled at about 17,500 miles per hour. The Apollo missions, at their fastest as they fell back toward Earth from the Moon, reached about 25,000 miles per hour. The fastest human-made object ever launched, the Parker Solar Probe on its closest solar approaches, reaches about 430,000 miles per hour. That record is held by us, by the ingenuity of human engineers who figured out how to use the Sun's own gravity as a slingshot. But Parker Solar Probe achieves that speed because it's falling almost directly toward the Sun from a great distance. Take away that gravitational assist, and the fastest human-made object in deep interplanetary space is orders of magnitude lower. The Voyager 1 spacecraft, the most distant human-made object, now more than 15 billion miles from Earth, well into interstellar space, is traveling at about 38,000 miles per hour relative to the Sun. That's fast. Impressively, astonishingly fast, given that it was launched in 1977 and has been traveling for nearly 5 decades. But it is still less than 1/3 the speed at which 3I-ATLS was cruising when it first showed up on our instruments.
And here is the thing about 3IA Atlas's speed that is perhaps hardest to fully absorb. 137,000 miles per hour was not an unusually high speed for that comet. That was just its normal speed, the speed at which it was traveling through interstellar space before it even reached our solar system, before our Sun's gravity had added anything to its momentum. That is the speed of the galaxy. That is the kind of speed at which icy rocks drift between the stars.
As 3IA Atlas fell inward toward the Sun, gravity accelerated it further. By the time it reached perihelion, its closest approach to the Sun, on October 29, 2025, inside the orbit of Mars, it had accelerated to approximately 153,000 miles per hour, about 250,000 kilometers per hour, 69 kilometers per second. At 153,000 miles per hour, you could travel from Los Angeles to New York in roughly 1.3 seconds. You could circumnavigate the Earth at the equator in about 9.5 seconds. You could travel from Earth to the Moon in about 1 hour and 35 minutes. You could travel from Earth to Mars at average distance in about 3.5 days. You could reach the Sun from Earth's orbit in about a day. And yet, and this is the number that really puts the scale of interstellar space into perspective, at 153,000 miles per hour, it would take 3IA Atlas approximately 18,000 years to reach the nearest star system to our Sun. Alpha Centauri, the closest stellar system to Earth, at about 4.37 light-years away, is so far that even this extraordinary speed is essentially negligible on the scale of interstellar travel. The distances between stars are not just large, they are vast in a way that seems to deliberately mock every unit of measurement we reach for. They are vast in a way that makes the word vast feel inadequate. And 3IA Atlas had already crossed those distances. It had been traveling through those impossible distances for what we believe is billions of years, since long before our solar system existed possibly, since long before any of the atoms in your body had been assembled into anything resembling life, since before the Earth was even an idea in the gravitational evolution of a slowly condensing cloud of gas and dust. A billion years is 1,000 million years. In a billion years, the tectonic plates of Earth move about 4,000 kilometers. The Himalayas, the highest mountain range on Earth, have been built by about 50 million years of continental collision. Human civilization in its entirety, from the first cities to the present moment, spans about 5,000 to 10,000 years. Written language, our oldest records, dates back perhaps 6,000 years. And 3IA Atlas has been traveling through the dark for something on the order of 1 billion years or more. Let that sit with you as your breathing slows. 1 billion years of solitary travel through the cold between stars. And then, by the most extraordinary coincidence, or perhaps by the simply inevitable logic of a galaxy full of wandering comets and a solar system inevitably in the path of some of them, it passed through our neighborhood at exactly this moment in time, when we had telescopes that could see it, when we had spacecraft throughout the solar system that could study it, when we were alive to wonder about it.
Part 6. Where did it come from? After the initial excitement of the discovery settled slightly, after the orbital calculations confirmed the hyperbolic trajectory and the designation 3I-Atlas was officially assigned, astronomers turned to a question that was simpler to ask than to answer. Where did it come from?
The direction from which 3I-Atlas arrived, working backwards from its observed trajectory, points toward the constellation Sagittarius, specifically toward a region near the galactic center. The celestial coordinates of its incoming direction, what astronomers call its radiant, are roughly consistent with an origin somewhere in the inner galaxy. But here is the complication. The galaxy rotates. Every star in the Milky Way is in motion, orbiting the galactic center at some speed and in some direction. Our Sun takes about 225 million years to complete one full orbit of the galaxy. Other stars orbit at different speeds. Everything is moving relative to everything else. When we trace 3I-Atlas's trajectory backward through time, accounting for the motion of the Sun and for the gravitational perturbations that would have affected the comet's path over millions of years, we can narrow down the region of the galaxy it most likely came from. But because of the gravitational complexity of the galaxy itself and the enormous timescales involved, we can't identify a single star or stellar system as the definitive origin. What we can say is this: 3I-Atlas's velocity relative to the Sun, measured before our Sun's gravity had any significant effect on it, what astronomers call the hyperbolic excess velocity, was about 58 kilometers per second. That is exceptionally high. Oumuamua's hyperbolic excess velocity was about 26 kilometers per second. Borisov's was about 32 kilometers per second. 3I-Atlas was moving more than twice as fast as Oumuamua relative to the Sun's position in the galaxy. This high velocity provides a clue. Stars in the Milky Way have a spread of velocities relative to the Sun. Most nearby stars have velocities within about 20 to 30 kilometers of the Sun's velocity. But some stars, older stars particularly, or stars that have been dynamically scattered by gravitational interactions, can have velocities of 50, 70, 100 kilometers per second or more relative to the Sun. 3I-Atlas's high velocity suggests it came from a relatively old stellar population, a star that had been around for a long time and accumulated velocity through gravitational scatterings over millions of years, or a star whose velocity was simply different from the Sun's by virtue of being in a different part of the galaxy's structure. There are researchers who have attempted more specific calculations, tracing 3I-Atlas's path backward and looking for close approaches to known stars within the relevant timescale. These analyses are difficult and uncertain because the further back in time you go, the more uncertain the positions and velocities of individual stars become. Stars are moving, their positions shift. The data we have for stellar positions and velocities is excellent but not perfect, and errors accumulate over millions of years of backward projection. Some teams have identified candidate source stars, systems that might have been close enough to the object's inferred trajectory at some point in the relevant past. But none of these identifications is definitive. The honest answer, the scientifically accurate answer, is that we don't know which star 3I-Atlas came from. We may never know with any certainty. The galaxy is large, the timescales are enormous, and the data we have for reconstructing stellar motions over millions of years is simply not precise enough to point to a single culprit. What we do know is what direction it came from, what speed it was traveling at, and, from its chemistry, which we'll explore in detail, something about the conditions in the star system where it formed. And those chemical clues are in some ways more informative than any orbital reconstruction could be. Because the ice of a comet is a fossil, a frozen record of the conditions under which it formed. The ratios of different molecules, the proportions of different isotopes, the abundances of different volatile species, all of these encode information about temperature, pressure, radiation environment, and chemical composition at the moment the comet's material condensed from gas into ice billions of years ago in some protoplanetary disk we've never seen. 3I-Atlas was bringing us a chemical letter from another solar system, and the instruments we had at our disposal in 2025 and 2026 were sophisticated enough to